So I'd left off last time introducing you to the idea of a charge density, a charge per unit length, a charge per unit area, charge per unit volume. And the process of doing this, we end up creating a variable, which is our charge density variable, and I want a different color. We have our charge density variable, which is essentially defined as the total amount of charge divided by the total amount of length. So this way we can describe the charge as a charge density times a length. Now, the charge density can be non-uniform. It can be smaller on one end, larger than the other, but we're not going to get into that. We're just going to assume that the charge density is constant. It's the same at all locations. So no matter where I pick, if I pick right here or I pick right here, I have the same charge density or charge per increment of length, no matter where I go on that particular object. And because I can then shrink the size down to an infinitesimally small size, making it effectively a differential, I can rewrite my lambda as a derivative, meaning it's dq dx. But taking a derivative, we can break it into its pieces, where we refer to it as differentials. Now, you guys may have forgotten what differentials were from Math 140. Essentially, they're just increments of a particular variable. You ended up using them, I think, for about 10 minutes during your Math 140 class. But essentially, that's one thing we can do. We take the derivative, split it into its two pieces, and refer to them as differentials. A element of Q is equal to an element of length times this constant relation between them, which is the linear charge density. So we can do the same thing with the surface charge density. It's just the charge divided by the area for a square or rectangular area, length squared or length times width. Now, when we talk about in terms of a derivative or differential, the sigma here is listed as the amount of charge per area. Now, an area can be an increment of x times an increment of y. So in other words, you can have a dy component over here, and you can have a dx component over here. And so your increment of dx, your increment of dy, essentially multiplied together gives you an incremental area. And this allows us to set up a double integral, which is an integral of dx and dy. So this is something you run into in Math 251. And we're not really going to go into this, but I just wanted to point this out to you that an area, because it has two coordinate axes, therefore must be a double integral. And then the third one is, well, actually, the area can also be a circular area, in which case the area is pi r squared. That's the area of a circle. So our total charge is now distributed over this circular area, and it's multiplied by this constant sigma. And our increment of d area is just the derivative of pi r squared. So you end up with 2 pi r dr, and that gives us this alternate way of writing dq for a circular surface. And then rho is now a volume arrangement, q divided by the total volume. This happens to be the volume of a sphere. This irregular shape would have some other value. But that particular equation is specific for a sphere. And so you take the rho is equal to dq over the volume. You take the derivative of 4/3 pi r squared, you get 4 pi r squared dr, and that gives you your volumetric differential for volume. Okay. So that being said, if this were any other semester and we had time to go through this, we would talk about the process of finding a continuous charge. I'm going to demonstrate it, but I'm not going to require you to know it. So don't worry about this process. There are, however, a couple of versions of it that we're going to want you to know. And those versions will be the straight line with P at some perpendicular distance to the straight line. That is essential because that's going to come up repeatedly. The surface of a disk is also essential. That's going to come up repeatedly. And then the ring is then the third one I'm going to ask you to know. So what all of these have in common, the single thing, is that we take the electric field of a point charge and we simply make an increment of electric field for some increment of charge. That's our beginning. That's how we start with all of these. So what I'm going to do now is I'm going to walk you through an example of a straight line charge, show you step by step the process we're going to do so that you are familiar with what the method is. And then we're just going to go right to the conclusions. What are the final results that we're really interested in doing? So the idea is this. I have a line of charge, and sitting on that charge is some amount of charge called Q. This rod has a total length of L, and I want to know what is the electric field at some point P perpendicular to the surface, right? So I need to come up with a distance from that charge to the surface. I'm going to call that distance A. And because I've chosen that particular location, I will now make this my origin. And I'll make this side negative L over 2. And I'll make this side plus L over 2. Almost. Okay, so I have the beginnings of a setup. The next thing I'm going to do is I'm now going to pick a small increment of my rod, some infinitely small increment. And I'm going to label this increment of a thickness dx. And I'm going to say that on that increment, there is a certain amount of charge, which is going to be dq. My next step is I'm going to draw a line from the dq to point P. And following that, I'm then going to draw the electric field vector that I would expect to see. So this is now my dE. That is my electric field vector at point P because of this charge. So take note of the fact that I have set up a right triangle. And that right triangle will have a hypotenuse that I'm going to label as R. And I need a label for the horizontal axis. I'm just going to call that X. So now I have a triangle with 3 sides. And my next to last element is I need to have a angle theta. Now I can pick the upper angle, I can pick the lower angle. It doesn't really make a difference, but I need an angle theta. Maybe I can draw that just a little bit better. There we go. Now that angle theta will be matched by this angle here. And as a result of that, I can now separate my dE into 2 components. I can make this one my dEx. And I'll have this one to be my dEy. which means I can now essentially erase that original dE. Okay, so I've set up a right triangle. I've set up an electric field direction because of my increment of charge. I've broken it into its X and Y coordinate axes. Now my next step is I'm going to begin with this expression. I'm going to start with E is equal to KQ over R squared. I'm going to then convert that to dE is equal to K dQ over R squared. And I want to integrate this expression, this dE. I want to integrate that in order to find the total electric field. Now, the K is a constant. That's a piece of cake. But the Q is not just this in point. I want to add up all of the dQs. I want to add up the dQs here. I want to add up the dQs here. I want to add up the dQs here. But Q is not a variable that I can integrate over because this increment of dQ, infinitesimally small as it is the same at all points. But what I want to do is I want to re-express dQ into a function of X. I want to turn dQ into a function of X. And I also want to turn R into a function of X. That way I can then integrate over X. And with that, solve for these elements. So what I need to do is I need to recognize that lambda is equal to dQ dx. Therefore, dQ is equal to lambda times dx. So dQ gives me my variable of integration dx. I have R is equal to the square root x squared plus a squared. So I've now converted R into a function of X. I'm on my way. But my next component here is I need to take my dE, and I have an X component and a Y component. They are different. And so I need to take into account the fact that based on my triangle below, cosine theta is equal to adjacent over hypotenuse. It's equal to A over R. And sine theta is equal to X over R, which is opposite over hypotenuse. Okay, so now I have my pieces. So I'll now write dEx is equal to K times lambda times dx times sine theta over R squared. I should just do it this way. And I can draw a line. All right. So I've converted my dQ. I still need to convert my lambdas. So I will keep going and make this equal to K times lambda. We'll put a space, and I'm going to put dx times x over square root, actually here, square root x squared plus a squared. Now that whole thing will have to be squared because it's R, basically. And then I have another one, which is going to be times the square root of x squared plus a squared. my line here, put my line there. Well, the dx should have been with the lambda, but either way, it's all going to get combined. And so now what we end up with is equals k times lambda. I'm going to put a space, and I'm going to put x times dx divided by x squared plus a squared to the power of 3/2. I'll stick a line under it. And so this ultimately is what we're going to then get. So E is equal to the integral of dEx E sub x So essentially, we're going to take the integral of dEx. We'll take the integral of this. We have k times lambda is a constant. Both of those do not, both of these do not, because they're constant, they can pull out to the front of the integral. They're not part of the integration. So my bounds will be minus L over 2 to plus L over 2. And now I've set up my integral. So this is one of the things that you started to do at the end of Math 140 when you did volumes of rotation. You were introduced for the first time the process of creating integrals or setting them up. But this is another version of this. So for those of you who are taking Math 141 now, you may not have run into this yet. This is a trigonometric substitution integral. It's a time-consuming and tedious process. Normally, I wouldn't ask people to do it because I give the process of, I give the setup and solution for this on the equation sheet because all I'm interested in is that you can set it up. And so that would be the algorithm I would normally have asked you to do, is to set up this diagram. And based on that setup, you then get this result. You get this component here for the y-axis. Hang on for a moment. Seem to be missing something. Oh, I see what I did. Ha ha ha. All right, am I sharing my screen here? What's going on? I'm not. Okay, so this is the x-axis. Forgive this. This should read x, not y. So there's the integral we just set up with a missing dx in it. So that's your setup. Your solution looks like this. When you plug in the plus L over 2 minus L over 2, you end up getting this expression. And as a result, the expression here on the left side and the expression here on the right side are exactly the same. You're subtracting them, and as a result, you end up getting 0, right? Nothing adds up on the x-axis. Now, we can recognize that from this diagram, because if I were to take a look at the contribution from the dqs on the left side, which would have a line going this way, which would have a DE going out in this direction, the X components would cancel, right? The Y components would add together. You can just see that visually. And so you can just declare the symmetry of it by stating the two cancel, right? Now that we've got that, we do the y-axis, which is now KQA over L. It's 1 over x squared plus a squared to the 3/2, so it's missing the x. We solve it, we get this expression. We plug in the plus L over 2 minus L over 2. We get this fairly complicated expression, but we note that the L in the numerator will cancel the L in the denominator. The 1/2s, I have a minus 1/2. I'm subtracting a minus 1/2. They add, therefore 1/2 plus 1/2 is a whole. And I end up with this expression at the end of the day. So this is my final expression for a finite wire. So what I need you to be able to do is to recognize that A is the distance perpendicular from the axis of the wire. L represents the length of the wire. Now, the question then becomes, what do we do to get this into a convenient form for us to properly understand the its practical everyday purpose, everyday use for us. So when we imagine the electric field of a wire, for most particles that are going to be affected by it, protons, neutrons, atoms, things like that, they are very small. So even a relatively short wire, when you get one of those tiny particles close to it, it's going to look like an infinite wire. So if we take the limit of this, we have two limits. The first limit is that the separation distance is much, much smaller than L, meaning something's very close to the wire. When we do this, the square root in the denominator becomes approximately L over 2. And as a result, our expression simplifies into 2kq over A times lambda. Now, the A is the perpendicular wire, but if we take the Q over L, that is equal to lambda. And now we get this expression, which can be written, if we want, as 2k lambda over A, right? That's, put in some time signs here. So that is a universal outcome for all wires. Generally speaking, when you're close to any wire or when any wire is sufficiently long enough, this expression pretty much governs the electric field near a wire. So this is the thing I want you to know, right? Write that down, memorize it, inscribe it on your equation sheets, but we'll be seeing this one again. And so this is our official, the electric field of a line is that. So that's the outcome I want you to know. And you've now seen the process of where it came from. So let's look at the other examples. Actually, let me do a visual. So if we have a rod with electric charge on it, essentially the electric field will be pointing always outward, radially from the axis, and it will be pointing inward if it's negative. So the arrows are always just essentially pointing away from the center of the wire. That's what this expression represents. Now, let me go back here. The other limiting case is that when you're very far from a long wire, the wire, it will essentially look like a point charge. Our next case is a ring. So we have essentially the same setup. We have a ring of radius r. We're some distance away from the wire. We set up our distance little r, which is the z squared plus r squared. We create our components of dE. The x and y's components will cancel. The z components will add. And when we put it all together, we get this terrifically cumbersome expression. So this is the electric field from a ring on the axis of the perpendicular bisector. So this line that goes through the center of the ring and stretches top and bottom above it, this gives us the electric field along that line and only along that line. And z represents the distance from the center, r represents the radius of the ring. So similarly, we have limits. As z approaches 0, when you get to the very center, E must be 0 because the electric field of all those round charges will cancel each other out in the center. As z goes to infinity, z is much, much greater than r. Therefore, z squared to the 3/2 becomes z cubed, and you end up with an expression that looks like a point charge. So in the far distance, all of these will end up looking like point charges when you get far enough away from them. Last one here is the disk. Again, we're looking at a complete area, a circular area. So we're going to break this up into circular rings. Each ring has a radius, which we're going to call r prime. The distance, little r, is from the ring to the point we're evaluating. And as you can see, again, the x and y cancel, only the z remains. And so we can take the electric field of a ring, multiply it by a thickness dr, and that gives us our increment of area, which is 2 pi r times dr. So not getting into the details, we're just getting to the final answer. This ends up becoming the answer to a single plate of charge. The electric field is equal to this expression, which is the surface charge density over the permittivity, divided by 2. Now, the 1 means that's 100%, and then the negative is essentially what we're subtracting as a function of distance. So z being the distance along the axis away from it. So again, similar to the ring, this is along the axis. I'm not going to be asking you to determine a point out here off axis. It can be done. It's just beyond the level of mathematics we're going to play with. We're doing high symmetry situations in order to demonstrate key features. All right, so that expression, as z goes to 0 or r becomes large, meaning you've got an infinite sheet, this is the thing to know, because this is going to come back a lot in chapters 7 and 8. This is the electric field for an infinite sheet. It's the surface charge density. So sigma equals Q over area, right? That's what the sigma represents. And so be aware of that. Now, the homeworks that you guys have for these problems, all of them can be done provided that you simply know what the, as long as you know this expression or the ring expression or the wire expression, there's no reason you shouldn't be able to handle any of them. Just make sure. Last part is infinite planes. So the surface, the electric field off of each of these is sigma over 2 pi, sigma over 2 epsilon. So between two sheets, they would add. You'd have one from the left sheet, which is positive, one from the right sheet, which is negative. They would add together and the factor of 1/2 would disappear. Okay, so that essentially ends chapter 5 and what I need to introduce you to for chapter